Sorry, I just learned that I can't start a recording if I'm sharing my screen. Okay, so let's try to get started here. Good morning, everyone. I hope that you're all doing well. So here we are into our second week of trying to get these classes together. So what I want to do today and Wednesday is start to get into what do we mean by a Cauchy sequence. And I figured instead of just jumping into a crazy definition of a Cauchy sequence, let me try to motivate things a little bit today, kind of prove a few things, go over some examples, but I do want to try to motivate all of this. So today I want to go over the concept of subsequences that I think that you'll need, not for the homework assignment on Wednesday, but for the problem set that we're going to do on Friday. And then on Wednesday, we'll start to go over the definition of what a Cauchy sequence is. So today we're just going to try our best to kind of motivate all of it, figure out what's happening, right? Okay, so let's just try to do some recap of where we were. So first, I'll just make a few of the standard announcements. On Friday, of course, we did a review of all of the 4 problem sets that we've done so far. So that review is now online on YouTube. I think that I accidentally called it Less Than 20, but I changed the name over the weekend. So now it's just called the problem set review. I have the office hours at the usual time, usual place. So if you have any questions whatsoever, just feel free to come by because I'm just sitting here and I'll be ready to answer any questions that you have. We do have the mentor sessions as usual from 6 to 8 p.m. Sunday, Monday, Tuesdays, and Thursdays. So if you do have any questions, Sharice will be there to help answer them. And then, of course, we do have the next problem sets and homework assignments that are due this week. Homework assignment number 10 is going to be due on Wednesday, and problem set number 5 will be due on Friday. So what I mean by due is that we're actually going to try to do it in class. We're going to try to do this over Zoom. I don't know how this is going to work, but the plan for Friday is I'll try to do some screen sharing. Hopefully you can kind of show your answers in this kind of way. I'll say that if you like to try to present your solution here, there is a way that you can do whiteboard in Zoom. If you wanted to write everything on a sheet of paper and kind of show it on your computer screen, that's perfectly fine as well. I'll just look for volunteers. If it does get to be too difficult, I'll maybe try to walk through some solutions if you have them. But this is the hope, that we'll try to do presentations for the solutions on Friday. Right, so I'll talk about it again on Wednesday, but that'll be the plan for right now. So any questions about any of the announcements here? Okay, all right, great. So let's try to move ahead. So let's do a recap of where we were then on Friday. As usual, let's let F be our complete order field, i.e. you can just think of this as the real numbers. So of course we have the concept of a sequence. So this just means a collection of numbers from F that are indexed by integers. So just the 0 as well as the natural numbers. We'll say that a sequence converges using the so-called epsilon delta definition. So it just says that if somebody gives you epsilon, then you can find a delta such that here this difference is as small as you'd like. Right? So this x minus L is less than epsilon. And then if this is the case, then we'll just write this symbol here. So the limit as n increases without bound of x sub n equals L. So again, this is just our epsilon delta definition of what does it mean to converge. Okay. Next, we said that a sequence increases without bound or decreases without bound if we have the following. So let me use the plus sign for increase without bound, and I'll use the negative sign for decrease without bound. So we'll say that our sequence increases without bound if given epsilon, we can find a delta such that xn is greater than epsilon, and decreases without bound means that given epsilon, I can find a delta so that negative xn is greater than epsilon. Right? That's the same thing as saying that xn is less than negative epsilon. It's exactly the same definition. So increasing without bound, decreasing without bound simply means this here, right? That we want to say that the limit as x increases without bound is plus or minus infinity. And of course, that's just what we mean by saying that the sequence diverges. That as n increases without bound, then xn either goes to plus infinity or xn goes to minus infinity. Right? Now, we also talked about the monotone convergence theorem. So I want to remind you of a few of the concepts here that we're going to need today. we say that a sequence has a lower bound if we can find an element A where A is less than or equal to xn for all xn in the sequence. Right? That's what we mean by a lower bound. Similarly, we say that we have an upper bound for the sequence if xn is less than or equal to b for all xn in the sequence. And of course, we say that our sequence is bounded if it has a lower bound and an upper bound. And we had a homework assignment that said that a sequence is bounded if and only if we can do this. Right? If there's some number m such that the absolute value of xn is less than or equal to m. Right, so we're going to use this crucially today. So again, a bounded sequence means that I can find an m such that the absolute value of the terms is less than or equal to m. Right, so any questions about this up to this point? Okay, so right now just doing a review. Next, we said that a sequence is monotone increasing if the next term in the sequence is greater than or equal to the previous term in the sequence. So xn plus 1 is greater than or equal to xn. And we say that our sequence is decreasing if the next term in the sequence is less than or equal to xn. And of course, we'll say that our sequence is monotone if it's either monotone increasing or monotone decreasing. I'll just kind of throw this out here. Some books won't want you to put a less than or equal to. They just want you to put a greater than or equal to. They just want you to put in a greater than. Similarly, they don't want a less than or equal to. They just want a less than. It actually doesn't matter from the theorems that we're going to put here. This is the same thing of what does it mean to be a divergent sequence. That all of the different theorems that we're going to prove here work regardless of whether you have a less than or equal to or strictly less than, a greater than or equal to or strictly greater than. All of the theorems hold in exactly the same way. So of course, our big theorem is the monotone convergence theorem that says that if we have a monotone sequence that is increasing, then either it converges or it diverges. So of course, if it has an upper bound, it will converge to a number. If it does not have an upper bound, then the limit is plus infinity. Similarly, if it's monotone decreasing, if it has a lower bound, it converges. And if it does not have a lower bound, then it goes to negative infinity. Right? So that's the monotone convergence theorem. So it just simply says if you have a monotone sequence, either it converges or it diverges. Right? One of those two. Right? Okay, questions so far? Okay, so we have all of this now. Now, let's just kind of stop for a minute. Let's maybe take a look at some numbers. And I want to go over a motivating example today to try to get into what are some of these crazy theorems that we're going to get into this week. So the monotone convergence theorem gives us a nice criteria for determining when a sequence converges or diverges, very specifically when a monotone sequence converges or diverges. So what I want to know is what happens for a very general sequence. So if somebody just gave you a collection of numbers, is there a way that you can easily look at that sequence and say, oh yeah, it's convergent? Right? That's really our big motivating question. If somebody just gives you a sequence, can you just look at it and just know it has to converge to something? So kind of as a test, let's take a look at this here. I introduced this in class a few weeks ago. This is what's called the logistic equation. So here I want to write down a sequence recursively, defined in this way here. So the next term in the sequence looks like rho times xn times 1 minus xn. So rho here is a real number. And I want to try to figure out what can I say about this sequence here. So let me first write down a couple of facts, and then we'll come back and we'll try to work out some specific numbers. So the theorem here says, let's choose a real number rho between 1 and 4. Right, so fix any rho that you want that's between 1 and 4. And let's define the sequence in this way using the logistic equation. Right, so xn here looks like rho times xn times 1 minus xn, where rho is just any number between 0 and 4. Sorry, 1 and 4. Any number that you want between 1 and 4. So first of all, if my starting point is between 0 and 1, then every term in the sequence is between 0 and 1. Right, so again, if I start with some x0 that's between 0 and 1, then every term in the sequence is between 0 and 1. So what this actually says is, if I start between 0 and 1, then I have a bounded sequence. Right, so this kind of gets back to this definition that we had of a bounded sequence. So here I have an upper bound, I have a lower bound. So if I know the first element in the sequence, then everything else here will be bounded between 0 and 1. On the other hand, if my starting point is either 0 or 1, then every term in the sequence is exactly 0. So what the second part here says is, let's maybe stay away from the endpoints. So I don't either want 0 or 1. So I'm just going to stay away from those two, because if I do have those two, 0 or 1, then I know every other term in the sequence. Right? So I'm going to put all of this together to say that I'm going to think of this function. So if I start with an x, then I can write down a new number, rho times x times 1 minus x. What it does is it takes a number between 0 and 1, and it gives me back another number between 0 and 1. Right, so this is like some weird kind of iteration. So if I start with something between 0 and 1, I plug in this formula, I get back another number between 0 and 1. So this kind of explains why I want my rho to be a real number between 1 and 4, because then now I can have this iterative process. Right? Does this kind of make sense so far? Okay, so we are going to do some examples here. I think for the sake of time, I am not going to worry about going over the proof of this. So I'll just say that you can actually prove all of this by induction. If you wanted to see the proof, you can just go ahead and read it in the lecture notes, but I'm not going to worry about the proof because it's really not crucial for what we want to talk about today. Okay, so let's try to do some examples now. So what I'm going to do is let me maybe pull up Mathematica, and then I'm going to try to do some programming here in real time so you can see how some of the numbers here work. All right, so let me open up my Mathematica window. So give me just a moment here for this to load. And then we'll try to just play around with some numbers. Okay, sorry, give me just one minute here. I didn't realize I have too many windows open, so it's hard to kind of figure out what's what. Okay. Stop sharing here. I'm going to open up my Mathematica window here. Okay, what we're going to do is define a sequence by doing rho times xn minus 1, 1 minus xn minus 1. Right, so that's going to be my recursive sequence. Right, if I start with an xn, then I know how to do the next term in the sequence. So for the moment, let's take maybe rho is equal to 1. And let's start off with our initial term to be maybe, let's say 1/3. Right? So then what this does here is this is just going to generate a whole lot more numbers. And here I just want to see what this looks like. So let's do maybe xn here. Let's do maybe n goes from 0 to 10. And I actually just care about the numerical values so I can see this a little bit better. And let's put this in a table so we can actually see it. Right, so again, all that I'm doing here is I'm just going to generate a table on the fly so I can kind of see what some of the numbers here look like. Okay. All right, so this over here is my n, right? So n goes from 0 to 10. And this over here is my x sub n, right? So like this here would be x0, that's x1, this is x2, x3, so on and so forth. Right? So does anyone want to make any comments maybe on what you might see with the numbers so far, and any thoughts on what you're seeing here?
It looks like they're decreasing, but they start decreasing more slowly.
Yeah, that's right. Yeah, it definitely looks like the numbers are decreasing. So here I'm at 0.3, then 0.2, 0.17, then I go down to 0.1. Well, let's maybe try to increase this a little bit. Maybe let's try to go from 40 to 50, right? Just further out in the sequence. So let's just see what happens. I think that this is not going to be too hard here to do. So you know what? I think I know what the problem is. Let's try to quit out of this. Okay, let's try to maybe just do from 0 to 30. So that might be a little bit better. Sorry, I know exactly what the problem is. This is kind of a weird Mathematica issue. What it's actually trying to do is compute all of this as an exact rational number. And when it's doing that, it's getting really confused because the numbers are getting too big. So I need to change everything to decimals, and then it should run faster. Okay. I don't know why this is not running. Well, it doesn't matter because I have a backup over here on the slides. Let me maybe try to do another example here. So instead of 1, let's maybe just try to increase this to 2. Right? Just to see what will happen. Okay, so here we've increased to the number 2. So here is my sequence of n's. And now over here, these are my x of n's. So I start with a third, then here's x1, here's x2, x3, so on and so forth. So any comments about numbers that you're seeing here?
Heads towards 0.5.
Yeah, looks like it's heading towards a half. So in this case, it maybe looks like the sequence is slightly increasing, right? 0.3, and then 0.4, then 0.5. Right. Okay, let's maybe just try one more here. So let's try rho is equal to 3. And let's plug in this here. Okay, so any thoughts on what's happening here?
It's converging to 2/3, but does so more quickly than the others.
Yeah, that's right. Yeah, it does look like that this here is an increasing sequence and it goes to 2/3. So let me come back over here to the slides. So all the data that I have here I actually do have in the slides. And we can see what's going on. So here we had rho is equal to 1. And you can see that here we have n, right? So n here is increasing. And over here for xn, you can see that this is getting smaller and smaller, and it seems to be going to 0. So this is like what we said before. It's a decreasing sequence, so monotone decreasing, and its limit appears to be 0. Right? So this is rho is 1. So let's try here rho is 2. So here's another example. We just worked this out. So this now is increasing, but this here is going to a half. Right? So this looks like that the limit here is going to be a half. And then we just worked out rho is equal to 3. So again, this here is increasing, and it looks like it's increasing so that the limit here is going to be 2/3. Right? Does that make sense? Okay, so we're just playing around with some numbers here. So here we started with rho being between 1 and 3. Let's try some really crazy examples here. Now let me try rho is between 3 and this number here. 1 plus the square root of 6. So can somebody tell me numerically what does 1.1 plus the square root of 6 look like? Numerically, what is that?
It's irrational, right?
Right, it is irrational. But say like in terms of a decimal, like roughly what is that number?
Like 3.45-ish?
Yeah, about 3.45-ish. So let's maybe try to find a row between 3 and about 3.4, right? Just to get an idea. So I'm going to stop sharing again. Let me come back over here to Mathematica. And same thing as before, let's just play around with the numbers. Let's just see what happens. So let's see, well, we just did 3. Let's maybe try 3.1. Right, so we're going to try something between 3 and about 3.4, 3.45. So let's try to do this here. Okay, so here's my n, and now here are my x's. Okay, so any thoughts on what you're seeing here? Any comments?
Seems like there's no certain patterns. They're just going up and down somewhere between 0.69 or
Yeah, that's right. There doesn't seem to be a pattern here at all because, like, at one point, this is like 0.65, then it goes to 0.69, then 0.65, then 0.7, then about 0.65 again. So here, I don't know if this is going to work. I don't know why my mathematics is acting weird. Let's try to just run this a little bit further out. I don't know why this is not. There it is. Okay, so again, here's my n's. So now we can maybe see this a little bit better. This doesn't seem to be converging, right? Because on the one hand, this is like a 0.62, 0.72, 0.61. So it's almost like it's jumping back and forth between two different numbers. Right? Is that kind of makes sense here? Okay, well, let's try this. Let's maybe try 3.2. So let's see what happens here. Right, so 3.2. Now let's just try to run everything from 0 to 20. So here are my n's. Okay, so any comments on what you're seeing here now with the xn's? Yeah, let you kind of stare at it. Just tell me whatever comes to mind when you're looking at this. Yeah, Lawrence, do you want to say something?
It seems like it's jumping between two numbers, but those numbers are getting further apart.
Right, that looks right. So let's see, so here's like 0.54, 0.79, 0.52, 0.79, 0.51, this is almost 0.8. Right, so it's definitely jumping back and forth between these two numbers. Okay, let's maybe just try one more here. Let's try 3.3. Right, and then same thing, we'll just run this for the first 20 terms in the sequence. Okay, so now any thoughts on what you're seeing here? Right, so
Again, it's like kind of jumping around.
Mm-hmm. Yeah, it's jumping back and forth between these two numbers. Do you see any pattern here, maybe about how the index n is related to the two numbers that it's jumping back and forth between?
to me it seems like for odd indexes they're going to 0.82 something, and for even indexes they're going to 0.47. But like those, if you take apart even and odd indexes, they're still going up and down the number.
Mm-hmm. So let's see here. So I'm going to do a little trick here in Mathematica. I'm going to do a statement here. This means look at a list. N goes from 0 to 20, but step it by 2. Right, so let's see maybe what happens if we just pull out like the even ones. So now, can you see that a little bit better? So it definitely looks like the even ones are starting to approach some number, maybe like 0.479 something. right? I mean, we can't necessarily say it's increasing because it kind of starts low, then it goes high, then it kind of comes back down again, right? But at the very least, it does look like it's tending towards something. Let's maybe try, what if we just did the odd numbers now? So I'm going to start going from 1 to 20, and again, I'll step by 2. So now the odd numbers seem to be approaching to maybe something like 0.82. Right? And does this kind of make sense here, what we're saying? Okay, well, let me come back here to the slides, and let's try to put all of this together into one place. So again, here we're just looking at very specific numbers. So we can take a look at 3.1, just like what we did. We can also look at 3.2, and we looked at 3.3. So here you'll see that there isn't really a clear pattern of where the numbers are tending to. But if you go further out in the sequences, so let me come back to 3.1, and now I'm going to go further out. So now let's go from 40 to 50. And you can really see it's jumping back and forth between two numbers, right? So let's say here for the even ones, it looks like it's about 0.55801. For the odd ones, maybe circle this one here, it's about 0.764. Right, so it's definitely jumping back and forth between two different numbers. Right, we can also see that over here when we had 3.2. Right, so again here, we're kind of jumping back and forth between two numbers. So we saw that if we just look at the even indices, that's approaching to one number, versus the odd indices seem to be approaching a different number. Right, and then the same thing for 3.3. So it said it looked like the even indices were approaching 1, and the odd indices were approaching something different. Right, so does that kind of make sense, what we're seeing here with some of these numbers? Okay, so let me use all of this. I'm going to now present some definitions, and I want to present a very general theorem. So we just got finished saying that numerically, if rho here is between about 3 and about 3.45, there are two different sequences. So one here corresponds to the even indices, and one here corresponds to the odd indices. Right, so again, within that sequence, we actually found two different sequences. And so here's the theorem that I'm not going to worry about proving, because this theorem is not easy to prove at all. So again, let's say that we have this sequence, and let's consider rho between 1 and 4. So first of all, if rho is between 1 and 3, then the sequence converges to this quantity here, rho minus 1 over rho. So this is why we said when rho is equal to 2, this looks like it approaches a half. And when rho was 3, it looks like it approaches 2/3. Right, so this is a very general theorem. If rho is any real number between 1 and 3, then this sequence converges to rho minus 1 over rho. Right, and again, we're not going to worry about proving this because the proof here is not easy at all. But now, what if we're in the second crazy case of rho between 3 and this 1-point radical sets? Right, so again, we're going to be in the second case here, where rho is between these two numbers. So first of all, the set A does not converge. And I'll try to explain why in a minute, why it doesn't converge. So what we'll do here is, let's take a look at these two sequences, B, which corresponds to the even terms, and B prime, that corresponds to the odd terms. So the theorem is that the even terms tends to this limit. So this is involving a square root, whereas the odd terms correspond to this limit, which corresponds to this square root. The simple difference is one is a plus something, one is a minus something. So again, the even terms approach to one of them, whereas the odd terms approach to the other one. So here's the crazy thing. If I restrict to just the even terms, that will tend to one limit. And if I restrict to just the odd terms, that will tend to a different limit. So this means that the sequence A cannot converge, because if it did converge, it would have to converge to one number, one limit. But these here are two different numbers. So that's why the set A cannot converge. So here's our first real example here in the class of a sequence that does not converge. So it's not that it diverges. In fact, this is the sequence that's even bounded. But I still have a bounded sequence that does not converge. Okay, so this kind of makes sense for this example here. Okay. So we're talking here about this idea of that instead of looking at the entire sequence, we now take a look at kind of just very specific terms. So let's try to give all of this a definition now. Right. So I want to say, start with the sequence A. A subsequence is a subset of the sequence that is also a sequence, right? So subsequence is a portmanteau. It just means a subset that is a sequence. So remember that to be a sequence, it still has to have infinitely many elements. It needs to have one for every index. So here, let me take a look at the following, where my indexing set might be some new set here, P. So for example, P might be the collection of even integers. P might be the collection of odd integers. Right, so P here is just going to be some infinite collection of natural numbers. So again, P might be even integers, it might be odd integers. So instead of me indexing by every integer, by every natural number, I'm only going to look at an infinite subset of those. So that's what I mean by a subsequence. So I'm just indexing by some infinite subset of the natural numbers. Maybe not every natural number, but some subset thereof. Right, so again, kind of think of the previous two examples as this here. So like P might be the set of all even indices, or P might be the set of all odd indices. So the main theorem for today is this theorem by two mathematicians, and we're going to call this the Bolzano-Weierstrass theorem. It says, say that we have a bounded sequence A. Then A has a convergent subsequence. So with this proposition, I want you to think back to the previous example we just worked out. So in all of those, like when rho was 3.1, when rho was 3.2, then the set A was a bounded sequence, right? Because everything's between 0 and 1. A itself did not converge, but A had two subsequences that did converge. So again, that's the whole idea here. So maybe A itself might not converge, but it's going to have a subsequence that will converge. So for the sake of time today, I'm not going to worry about trying to prove this here. Let me just make a few remarks about this. This actually was first proven in 1817 by a mathematician named Bernardus Bolzano, and this was later discovered independently by a German mathematician named Carl Weierstrass. So this name here is actually a little bit weird, and I have to say I'm kind of picky about how to pronounce this because for the thesis defense I had for my doctoral work, the one issue my advisor had was in the way I was pronouncing Weierstrass. So I'm actually really picky about this now because I'm kind of a little bit traumatized by that. So this German mathematician, Carl Weierstrass, isn't really the first one to prove this, which is why it's a little bit weird that we're calling this the Bolzano-Weierstrass theorem when technically this was actually proven by Bolzano first. But I want to point out that Bolzano actually has a lot of influence on the way we're doing things here with this class. He's credited with being the first person to introduce the epsilon delta definition of a limit. So a lot of what you're going to see in analysis was very much inspired by the work that Bolzano did. Ironically, even though we say that Bolzano was a mathematician, he actually was a philosopher. And a lot of the writings that he had at the time, back in the late 1700s, early 1800s, really had to do with a lot of the philosophies he had about life and about logic and what have you. So a lot of analysis really is based in logic, which is why we spent the first half of the course going over like truth tables and what have you. Right? So again, this here is the Bolzano-Weierstrass theorem, and it just says that if you have a bounded sequence, then it has a convergent subsequence. So I'm not going to worry about the proof, but if you wanted to see the proof, it's here in the slides. It's also going to be in the lecture notes, but I think it's just not worth it for me to go over the proof here, just because it's going to take us a little bit far afield from what I want to say. So what I do want to do is spend the last 10 minutes or so actually going over an example of this to kind of explain what's really happening, how can we really use this Bolzano-Weierstrass theorem. So let's come back to the logistic equation. All right, so remember that for the logistic equation, we have this recursive formula here. So it says that xn plus 1 is rho times xn times 1 minus xn. And we're going to assume that our initial point is between 0 and 1. Right? Because again, if it's at 0 or if it's at 1, there's nothing interesting. So let's just start by saying it's between 0 and 1. And remember that the rho is anything between 1 and 4. So to start with, if rho is between 1 and 3, that's the nice case. Everything is really nice, right? So then A itself converges. So we don't have to worry about subsequences at all. We always have a bounded sequence. It converges. And in fact, this is what it always converges to. Right? So if rho is between 1 and 3, life is fine. Now let's increase rho a little bit, and let's say that rho is between 3 and about 3.45. So in this case, we worked out some examples, and we found that A does not converge. Right? It's going to jump back and forth between two numbers. And actually here we have two convergent subsequences. One corresponds to the even numbers, right, the even indices. The other one corresponds to the odd indices. And so in this case, then we found that the even indices tends to one limit, and the odd indices tends to a totally different limit. So in other words, there are two convergent subsequences. Right? Does that kind of make sense so far? Okay. Now notice that I haven't said anything about what happens if rho is larger. So what if rho is slightly bigger than this 1.6? So what I want to do is come back over here to Mathematica, and let's try to play around with this a little bit here. So let me stop sharing the screen, and let's just try to do the same thing we did before. Let's just play around with the numbers and see what happens. So here, I'm going to pick rho to be 3.5. And let's maybe go from 0 to 20. And let's just see what the numbers are. Okay. All right. So any comments and maybe patterns that you see here? We might have to go further out in the sequence. But first, do you want to make any comments about what you're seeing here? And while you're looking, I'll just start to run this larger because it's going to take a while. Yeah, so any comments whatsoever, just go ahead and take a look at it for a couple of minutes. Yeah, Lawrence?
Are there maybe 3 converging points in this pattern?
Well, let's see. So which 3 do you think you see?
I'm seeing 0.5,
Uh-huh.
0.82, and then 0.38.
Okay. Yeah, but what about the 0.87?
Oh, I didn't see that.
Yeah. But there's definitely more than 2. That's what it looks like. There's more than 2 here. Okay, and I'm trying to let the computer run so I can find more. I don't know if it's going to do it in time. So let me come back over here to the slides. And let's just look at things here. Right. So here's the data. So what I've done here is I've kind of gone so that, here's 0, 1, 2, 3, and then here's 4, 5, 6, 7, right? So I've kind of just started to run through the numbers. But tell me, what do you see when you see the numbers here? So here's all the xn's as n goes from 0 to 40.
It looks like there are 4 convergent subsequences.
Yeah, it does look like there are 4 convergent subsequences. That's right. So it looks like maybe when n is a multiple of 4, right, that's increasing up here to this number. Maybe when n is 1 more than a multiple of 4, it's increasing to this number here. When n is 2 more than a multiple of 4, this looks like this is decreasing. Right, so it starts at 0.6, then it goes down to 0.39, then it gets smaller and smaller and smaller. And then when n is 3 more than a multiple of 4, it also looks like it's decreasing. So this is kind of a crazy thing now. So now I have 4 subsequences. 2 of them are increasing to a number. 2 of them are decreasing to a number. Right, so let me try to say that here. So again, we have these 4 subsequences. And it looks like 2 of them are monotone increasing. And then 2 of them are monotone decreasing. So I put this example out there to say that this is actually a really crazy example, but this still tries to hit home what the Bolzano-Weierstrass theorem says. So A itself in this case does not converge. Right, A itself definitely does not converge to any one number. But notice that I can still write these subsequences. So within the subsequences, they will converge. But notice that I might have more than one subsequence. It's like in this case, I will have actually 4 different subsequences. So it's not just saying that there's exactly one, but you can certainly have crazier things happening. You can have things like this. So what I'll say here, just to kind of end things up, is that the logistic equation actually is a really interesting system, because what this says is if rho is between 1 and 3, there's exactly 1 limit. If rho is slightly greater than 3, but at least less than 1 plus the square root of 6, there are 2 limits. If you increase it, like what we've done here, to 3.5, there are going to be 4 limits. And actually, you can keep going. If you increase it a little bit more, there'll be 8 limits, then 16 limits, then 32 limits. This is actually what's called period doubling. And you can actually have it to have as many different limits as you want. And the actual crazy theorem is, if you increase all the way up to rho is equal to 4, then you actually have infinitely many limits. And this is actually what's called chaotic behavior. So I would say that if you don't believe me, play around with this logistic equation and try to vary this number rho and see if you can see what happens. So I'm not going to say at what point you actually go from 4 limits to 8 limits, but you can actually keep playing around the rho here. You can actually see that you can get as many different limits as you want. So it's always going to double the number of convergent subsequences that you have. So it will go from 1 to 2 to 4 to 8, so on and so forth. Okay, any questions on any of this before we call it a day here? Okay, all right, great. So then on Wednesday, the plan is I do want to introduce Cauchy sequences. We actually have a lot here that we're going to use to kind of motivate the definition that we're going to have. And then we're going to try to prove one of the big theorems, which is that Cauchy sequences converge. I'll just quickly say that in problem set 5, you actually are going to prove that, but we're going to prove it in a totally different way by using some statements in class on Wednesday. All right. Okay. Well, if there's no other questions, then you all have a good rest of the day and see you on Wednesday.
Thank you.
Okay. Take care.
Thank you.
Thank you.